In Unix, we have the concept of a link. It's reasonably important that you understand what a link actually is, because A, they're extremely useful entities, and B, there aren't that many operating systems out there that actually support links. It's unlikely that you would have seen a link before if you're not familiar with Unix. So, how do we understand links? Well, I'll start by saying that in Unix it is possible for a given file to have more than one name, and the various names that a file has can be scattered in various directories. What does that mean? Well, it means that if you've got a given file with some data in it, say the words "the quick brown fox," then that data file obviously has a name in some directory. Perhaps it's called file1 in the dir1 directory. Please understand that it is possible that that same data could have another name. Say it could be called file2 in the dir2 directory. So we can have two names, or two file names, in two totally different directories, and each is a reference to the same data. In other words, if you modify one and then go in by way of the other name, you'll find the data has modified there as well. If you don't believe me, allow me to demonstrate. There's a file in this directory called cat. Let's have a look at it. I'll just cat and see what I get. The quick brown fox jumps over the lazy dog. Okay, now I'm going to go into subdir1, and there is a file in here called fish. If I cat fish, I find out that it contains exactly the same information. But is it the same file? It contains information, but it could just be a duplicate of the original file called cat. Okay, well, I will now go in and modify fish using vi. And I will add another line. This is another line. Okay, and I'll save the file and quit. And I'll cd up into the parent directory where I will find the cat file, and I will now display the contents of the cat file. You can see very clearly that what I entered into the file called fish is now displayed in the file called cat as well. In fact, they are the same file. They just have two different names. Okay, I guess that's a reasonable enough proof that it's possible. Each of these names is called a link. We can say that that particular file has two links. Each link shares the same data. Each link also shares the same inode. So there's only one inode. There's one set of data, in other words, there's one block, and there's also one inode. That obviously means that each file, each link to the file, if you like, shares the same permissions. If you change the permissions on one, you're changing the permissions on the other one. If I choose to make one of them read-only, the other one becomes read-only as well. I can't change one independently of the other. Now, I want you to understand that as far as links are concerned, there is no original and there's no copy. Certainly we can create another link to an existing file, but once we have created the second link, and there are two links to the file, neither of them is considered to be the original. We're making the other one the duplicate or the extra link or something like that. They're both considered perfectly equal in all regards. This might seem a little odd, especially if you have a file and you create a second link to that file, and then you delete the original link. That you created simply continues existing without any problem around the fact that the first has been deleted. Now, I can't stress that strongly enough. Just about everybody, when they first encounter the notion of a link, believes that somehow the original is more important than all the duplicates. But I assure you that's not the case. Now, that is the case when we talk about symbolic links, but we don't know what they are yet, and we're going to learn about them later. Anyway, let's see how we go about creating and displaying links. Before we do that, it's very important to understand that when you're using the RM program, remember you think of the RM program as the program that deletes files? If you are deleting a file and there are multiple links to that file, and you try and delete one of the links, all that will happen is that name, that reference to the file, will be deleted, and all other references to the file, all other links, will remain intact. In other words, the file is still there. You just can't access it from where you were accessing it before because you've removed one of the references to it. So it's quite possible to delete a file and find that you get no extra disk space as a result, simply because there are other links to the file. So what happens is, when all of the links to a file have been unlinked, or deleted if you like, at that point the data is then deleted. And the way Unix deletes a file is the way most other operating systems delete a file. They simply mark that space, they mark that block as being now available for other files to use if necessary. So the implication of all of that is that any old file is simply a file that contains one link. If you create a file somehow, perhaps using Vi, it will simply be a file that contains one link. You can create as many links as you like to that original data, and even delete the original link or the original reference or the original name to that data, and the data will still be intact. We shall create some links in the next module, but before we do, I'll show you how you can examine how many links there are to any given file that you find. You can just use ls-l. We've been using ls-l now for almost the whole course, and it's been telling us how many links there are to each file that we see. We just haven't been paying attention. Let me show you. I'll now run ls-l in the normal way, and if you notice, the column immediately following the permissions is a column that contains mostly ones. That column is called the link count, and it tells you how many links are in existence for that particular set of data. For example, there is a file there called sample.html, it's third from the bottom. That has a link count of 1, which I can then use to assume that that name of the file, sample.html, is the only name for that particular set of data. However, if I look a little higher than that, I can see there's a file called cat. There's also a file called dog. Each of those has a link count of 3. That means that, for example, with the file called cat, that cat is just one of 3 names that that given file has. Where are the other 2? Well, they could be anywhere. It's often very difficult to tell. Note also that down towards the bottom we've got subdir1. Subdir1 has a link count of 2. Every directory that you see on the system will have a link count greater than 1. There is always at least one more link to a directory than the one that you can see. Can you think what the second link to subdir1 might actually be? Well, what if dir1 cd into subdir1 and do an ls-ld of dot. Look at the information that comes up. Compare that to the line, the second line from the bottom in the above listing. You can see that the permissions are the same, the link count is the same, the owner and the group are the same, the size is the same, and the date is the same. The only thing that's different is the name. One is called subdir1 and the other one is called dot. Remember I told you earlier that every directory that gets created has a little file in it called dot, which is an alias to the current directory. Well, now we can learn the technical term. Dot is just a link. It's a link that is automatically created for every directory. Why is it created? Just for convenience. So we are in both of the links to subdir1. In the course directory, the directory is known as subdir1, and inside subdir1, the directory is known simply as dot. 2 different names for the same entity. Now, you may have already noticed that cat and dog in this particular directory both have the same permissions, the same link count, the same user and group, the same size, and the same modification date. Are they the same file? Well, they might be. Or it may just be a coincidence. They may just happen to have all those things being the same. So how can we determine whether both of those files actually refer to the same data? Or, I'll put it more correctly, both of those names refer to the same data. Are those 2 files both links to the same thing? How can I determine that? Well, I've already given you the tools to know how to do that. You just have to think of it. Can you think? Okay, well I'll show you. I'm going to use the ls-i option, which lists the inode number. Clearly, if two files are actually referring to the same data, they have to share the same inode number. So let's do that. I use li, so I get a long listing, including the inode number. Whoops, I find myself in the subdir1. I'll try that again. ls-li. Better. Now, let's look at cat and dog. They both have inode number 2,662,370. They both have the same inode number, and that means absolutely guarantee that they are the same file. Which of course means that if I modify one, I modify the other. But if I delete one, the other one is still there, just with a diminished link count. Let's prove that. I'll just remove one of them. I'll remove dog. And I'll do an ls-li again. And I find that cat is still there, but its link count has gone down from 3 to 2. So there still is another link to cat somewhere around the place. And you may recall from an earlier example that it was the file called fish in the subdir1 folder, where that other link was. What if you looked at the link count and it said 17, and you go, oh gosh, where are the other 16 links? Is there any way of finding out? Well, the answer, really simple way of finding out. You can do it. It's actually quite easy to do, but there's no simple program that you just plug in an inode number and it tells you what all the links to that inode number are. You have to use the find program. And instead of, say, finding a given named file, you search for a given inode as follows. You type in find, followed by the directory in which you want to find, and then you specify the inode number using the inum flag. So which directory do you choose? Well, you would probably choose the root directory, unless you knew for a fact that all the links to that file were in a given subdirectory. So let's have a look at an example of that. So I might type find and then /. Now, I don't really want to search in the entire Unix file system, because that would probably take me a quarter of an hour or something, so I won't. I'll just search in the current directory, because I do happen to know for a fact that all the links to that particular file are in this subdirectory. And then I'll specify an inode number of, what is it, 2662370. And that will hopefully list for me all the inode numbers in the current subdirectory or any of its subdirectories that have that given inode. And I find that there are in fact 2 of them. Now I've found 2, and the link count tells me that 2 is the total, so I must have found both of them. I could remove one of them. I could remove subdir1/fish, and now I do an ls-l, and I find that the link count for cat has gone down by 1, but the file is still actually there. And now I can do an rm of cat, and that is the first and only time that the data in cat actually gets deleted. Just to prove that, I'll do an ls-l again, and it has completely gone. You don't see cat there with a link count of 0. Okay, so that's an understanding of how links work. In the next module, we'll look at how to create our own links.